Whereas coupling captured how connected classes and methods were to each other, cohesion captures the degree to which the members of a class serve a unifying task or concept. In this way, cohesion is much more about ensuring our program abstractions, and consequently our design is sufficiently well defined to allow related methods and fields to be placed together without being interfered with by other, unrelated code. We will also reason about cohesion in terms of a flowchart. Since cohesion is about the relatedness of elements within a class, we will start by a simple question. Does the class do one thing? This is a fundamental question because it means that a class should only be impacted by changes to just that one thing and not to any other aspects of the system. This will make the code easier to understand, maintain, and reuse. When a class is functionally cohesive, all of its code contributes to a single well-defined feature or task. The example here from Mario is functionally cohesive because it only really does one thing. It defines where on the screen a Starbucks should be placed and allows it to be activated by a figure. It's important to remember here that even though this code is highly cohesive, it's still coupled to the rest of the system, for example to star, figure, and item. Sequential cohesion arises when operations within a method transform output from one step and use it as input to the next step. This results in a sequence of steps oriented around some kind of data. Here's a different example from Coinbox within Mario. In this case, there is sequential cohesion because a number of steps are being performed linked by the coin object. This includes manipulating the Coinbox's items array, activating the coin, and adding the coin to the actor who hit the coin box in the first place. Sequence is important here too, because we need to bounce the box before showing the coin. This kind of cohesion is normal because these are the kinds of methods that allow our systems to perform complex tasks. Communication cohesion arises when different tasks are grouped together within a method only because they work on the same data. We couldn't find an example within our Mario code that exhibits communication cohesion, but this fragment shows what one might look like. Here we can see that the sequence of operations doesn't really matter. The commonality is all about performing similar actions on the this.data field. Ultimately, these first three kinds of cohesion are all part of good program designs because they show that the methods within a class are working on common tasks and data. Code is procedurally cohesive when it follows a specific execution sequence that is largely driven by control flow instead of data flow. In the code here, Mario's victory method is performing several different steps, but the order really matters. We have to play the winning music and show the winning animation before starting the next level, for instance. Again here we still see coupling to both level and view. Procedurally cohesive code is less desirable than our previous forms of cohesion because it is harder to independently reuse such code unless you are reusing all of the parts it is coordinating as well. Temporal cohesion arises when functionality is grouped only because it happens at the same point in the execution of the system, not because the functionality itself is related. This is problematic because it often results in actions on many different objects that are related only through the temporal semantics of when the method is being invoked. The example above comes from the level class, and here we can see a lot of manipulation of level, the world view, figures, obstacles, and items, even though the relationship between these elements in this method is just that we want to reset the level so we can start over. Logical cohesion occurs when different pieces of functionality are combined because they contribute to the same task, even if their intent is different. For instance, the set lives method in Mario exhibits a logical cohesion because while it might make sense for Mario to track how many lives he has remaining, it does not make sense for Mario to reach deeply into the level class to update the life count on the screen. In this case, the life displaying functionality would be better served in the level class itself rather than in Mario. For instance, if level changed its internal structure for displaying the life count, the Mario class would also have to be modified, indicating the change is not well isolated. Coincidental cohesion is the most detrimental form of cohesion and arises when functionality is arbitrarily grouped together. This form of cohesion is really the lack of any cohesion at all. It is terrible because it means that the code within a class will be harder to understand since it is responsible for a wide and diverse set of tasks. The code will also be hard to reuse independently and will be involved in many different bug fixes and feature additions, which increase the chances of defects propagating widely through the system. The Mario code was well defined, but the two methods above have been placed in the main file, even though they are no way related to that code. One common source of coincidental cohesion are classes with extremely generic names, like util. Thinking about how cohesive the classes are within our systems helps drive us towards designs that are easier to understand, debug, reuse, and evolve. You might recall that we said these were also the goals of loosely coupled systems, which is why you'll often hear that we want designs that are highly cohesive and loosely coupled. Because although coupling and cohesion are considering different aspects of our designs and implementations, they are both ultimately about improving the long-term quality of our systems.